Hi, and welcome to Fun with Flowers. Today we're going to talk about the motions of Earth in space, rotation, revolution. We're going to talk about why there are seasons on the Earth and why the sun rises in the east and sets in the west, but it's not always actually due east and due west, and we're going to talk about why. So we're going to start with the motions of the Earth in space. There are two words, rotation and revolution, and you need to know the difference between those. Rotation is the spinning on a central axis. This actually is orbiting around as it is spinning, but this represents rotation, the spinning on a central axis. If we're talking revolution, we're talking going around another body like this. And so one time around, let's say I start here and I end up here, this is one orbit or one revolution of the Earth around the sun. Rotation is as it's going around the sun, it is rotating. So let's talk about the time for one rotation and the time for one revolution on the Earth. So how long does it take the Earth to actually spin one time on its axis? Right, 24 hours, that's a day. And the period for one revolution is the time it takes to make one time around the sun, one orbit, which is 365.25 days. Now that quarter is important because after 4 years, 4 quarters equal 1. And we actually have a leap year. And today we had a leap year. We added February 29th to our calendar to make up for the fact that it does take 365.25 days to make it around the sun. So you need to keep in mind rotation, spinning on the axis, and revolution is going around another object. Now, with that in mind, I'd like to show you about the fact that the Earth is spherical. This is my friend, the Earth, is spherical. The sunlight hits it at different directions. So I have this flashlight. I'm going to shine it on this box. And notice how it's really intense right there. It's a small, intense, hot circle. Now I'm going to actually tilt this to represent what happens at the polar regions when because the Earth is a spherical shape. So we're going like this, and it makes it less intense, and it makes it spread out so it's not as warm. That's why it's not as hot in the polar regions as it is in the equatorial regions. So let's take our sun, and if I shine it right on his nose, it's very intense, it's hot, that's the equator. But and the sun's rays hit the Earth parallel, so as I move it up, notice that his forehead all the way to here is lit up now, so it spreads over a greater area, making it less intense. That's why the polar regions are cooler than the equatorial regions. It's because of the directness of the sunlight, or how indirect it is if it's being spread out over a bigger area. Now I'd like to talk about the sun and how it rises in the east and sets in the west. This is a solar motion model, and I'm going to set this for about 30 degrees because that's where Waco is located. Our latitude's about 32 degrees. And then this brad right here represents the sun. So you're going to watch where it's going, rising and setting. And then this is where a person is standing. So that's where you would be standing, and you would be seeing the sun coming up and going down in the sky. So we're going to set it at 30 degrees, and we are going to set it at what is called the vernal equinox or the autumnal equinox. Both of those happen in one in March and one in September. March is the vernal or the spring equinox, and September is the autumnal or the fall equinox. Equinox meaning equal days and equal nights. And that is the time of the year where, see where our sun is, it actually does rise due east and it sets due west. So we do have equal days and equal nights. Now, as we go from, let's say, spring, which is what we're doing now, and we move towards summer, I'll move my sun up here just to represent it. We're still at 32 degrees. Notice that the sun is now more north of east when it rises, and it's more north of west when it sets. it's actually up in the sky longer than it is if it's just moving east to west. And so this is actually the summer solstice in the northern hemisphere. It's different in the southern hemisphere. But in the northern hemisphere, it's our summer solstice, and it's our longest day. Now, it doesn't mean it's longer than 24 hours, but it means that it's our longest daylight hours when compared to our nighttime hours. So it's rising more north and setting more north of west. Now, let's go on toward our autumnal equinox. Rises in the east and sets in the west again, equal days and equal nights. And then as we go toward our first day of winter, which is the winter solstice, notice that now the sun's rising more south of east and it sets more south of west. And notice it's not as high in the sky. So that's another reason it's cooler. So rises in the east, sets in the west, but as the seasons progress, which means as the earth is going around the sun, the length of time the sun is in the sky differs. Now let's pretend we're at the polar regions. Okay, that would be, in this case, the North Pole. We're still standing here. This is where we'd be on the Earth at the North Pole. And look what happens. We'll leave it at the winter solstice. Look what happens. Does the sun rise or set? No. This would be darkness all the time for about 6 months. Okay, as we go in the year and move our way around the sun, we get to an equinox, and notice that the polar regions, that sun is right along the horizon. Okay, another reason why it's colder at that latitude. So it's right along the horizon. And then what do you think happens when we're actually tilted toward the sun? The sun never sets. And I think this is a really cool demonstration, a little squeaky, but it's a really cool demonstration of how the position of the sun changes based on your latitude. If we moved it to the equator, summer solstice, rises in the east, sets in the west. Move it to the equinoxes, due east, due west, and we move it to the winter solstice, and it's more south of east, and it sets more south of west. So with that, I'd like to do a demonstration with this. And this is my solar motion model. Sun, Venus, we're not paying attention to Venus. Earth, not paying attention to the moon. But the Earth goes counterclockwise around the sun. I need to make sure you can see it all the way through. There we go. Okay, the Earth is tilted on its axis at 23.5 degrees. Because of that, it receives unequal heating. Notice that this black thing right here is closer to the sun than it is when it's over here, and I'll show you that in just a minute. People tend to think that we have summer in the northern hemisphere when we're closer to the sun. That is not true in the northern hemisphere, because when the Earth is closest to the sun, we're actually tilted away from the sun. So that's where we don't get a lot of sunlight in the northern hemisphere. The sun's rising more south of east and setting more south of west. But as we move around, the angle that the Earth is tilted doesn't change. Notice this now is extended beyond this red part, which means we are actually farther in our orbit from the sun during summer. But the fact that we're tilted toward the sun means that the northern hemisphere is receiving the more direct sunlight. So it's important to know that it's that tilt of the Earth's axis that is the reason we have the seasons, and the fact that we're going around the sun. If the Earth was not tilted on its axis, then the North Pole and the South Pole would be receiving the same amount of light throughout the year as it's going around the sun. But since we are tilted, then at summer, it's receiving the more direct rays in the northern hemisphere. And as we move over here, the northern hemisphere is receiving less direct rays, kind of like what I showed you with the flashlight. Now I'm going to turn this a little bit so you can see the equinoxes, because here, this represents an equinox. And you can see that the axis is not tilted toward or away from the sun, it's kind of parallel to it, which means we have equal days and equal nights. All parts of the world are receiving the same amount of the energy from the sun as the Earth is rotating on its axis. So we have equal days and equal nights. We come over here, we're passing the winter solstice, the shortest day. Then we get to our autumnal, no, this would be our vernal equinox. We're not tilted away or toward. And then as we move here, then the axis of the earth is tilted more toward the sun. So we actually have our summer season. So you do need to know about the equinoxes. You need to know longest day, shortest day. There are 12 months in a year, 4 seasons, which means each season lasts about 3 months. So if this is our, let's get over here, if this is our winter, and that's in December, January, February, March is going to be our vernal or our spring equinox. Then we have 3 months later, April, May, June. That's going to be the first day of summer, our longest day. And then we go over here and we have our autumnal equinox, which will be in September. And then we move around and we're back to our winter solstice. Shortest day, summer, longest day. Hopefully that helps you with the seasons, the tilt of the earth on its axis, and why the sun rises and sets in the east and west and where it is. And until next time, thank you.